So this is the first example problem which we are going to solve using the method of superposition. So as you see over here, what we have is a cantilever beam which is partly loaded at the right end L/2 with a uniformly distributed load W, right? And what you see here, this is the standard table which has, for some of the standard cases, the expressions for the deflections and the slope and the equation of the elastic curve that is there. Now if you sort of scroll through this list over here, the only places where you have the cantilever beams are these guys over here. And if you compare with this one and this one, you actually don't have a case where you have just a part UDL. But the question is, can we make use, and the only beam that has a cantilever and a UDL is this one over here. So the question is that, can we use these relationships over here to solve this particular problem? So let's just go ahead and try doing that. So first I'm going to draw these beams as a superposition of two different beams, and then we will use this relationship which is given in this particular row of the standard chart to find the deflection and the slope. So let's first go ahead and draw the beams which when superimposed eventually gives back this beam over here. So what I have drawn, that in the first beam I have spread the UDL from the left end to the right end, similar to this one over here. So now it spans the entire length L, and to get back the original beam I must subtract the L which is at L/2 over here. It is this one. So this total length is L and this one acts over the span L/2. So let me go ahead and maybe mark that one over here, that so L/2, and eventually if you add these two beams you get this particular beam over here. Now to find the deflection and slope at B, so first let's so it asks at B, so at the end tip. So at the end tip, let's see, in this one it gives you the maximum deflection which happens at the end, Y max, as you see over here, that is this expression, and the slope at the end as this expression over. So that is pretty straightforward for the first one. And also let me write this one as beam 1 and this one as beam 2. So for the beam 1, I can directly use the table and write the deflection and slope at B. Now remember, eventually if I can find the deflection and the slope at the end B for this beam over here and add it to the deflection and the slope at the end B for this beam over here, I should get the deflection and the slope at B in the original beam. So let me first write for beam 1 directly from the table. So this is for this subscript 1 here refers to beam 1. So I've directly taken these values from the table and I've put it over here. And how does the beam 1 deflect, and how does it slope downwards? It slopes something like this. And you see for this beam 2, so now the beam 1 is fine. So next we have to find for beam 2. Now for beam 2, the interesting thing is that, you see, since it's a part of the cantilever only is loaded, so this beam, if you have to draw the deflection of this beam, it deflects with a slope over here, and after that, since there is no load, it is going to have a straight line. So let's just draw the deflected shape of this beam. Right? It has something like this. So it deflects up to here with a quadratic curve that is over here, and after that it continues like this over here. So now up to this particular point for this beam, I can find the deflection directly from this formulation over here. Remember, this formulation is valid for a length L. So when you have a cantilever with a length L, now the W starts from one end of the cantilever and continues up to the L over here. Here also, it starts at the 0 point and continues up to L over 2. And if you consider the beam as weightless, so essentially suppose this one does not have any weight at all, so up to this particular point we can get the deflection over here using this expression over here, but simply for L I have to substitute L over 2 over here. Simply here also the slope at this particular point, it is going to be WL cube by 6 EI, but for L I have to substitute L over 2 now, right? But now my question is that I'm trying to find the slope and the deflection at this point over here at B. So maybe let me go ahead and write those different points that are there. So this is A and this is B, and at the center point over here I have point C over here, and here also this is my A, this is my B, and at the center point over C, right? So I'm trying to find everything at this point B. Now you see that if this curves like this and then it continues like a straight line, the slope at C must be equals to the slope at B. So let's just quickly mark that one over here. So here whatever the slope that you will get, and the slope here must be the same. But what about, and if I find the deformation over here using this table, substituting L as L over 2, what about the deformation at this point? It can be easily calculated because I have a linearly increasing function over here with a particular slope. So let's just go ahead and maybe start to write that down. So all I'm interested for this moment is calculating what is my delta at C at this, in this beam over here, so in the beam 2, and also what is the theta at C for beam 2. So what is the theta? So this, remember this slope, so so this is the word slope, my webcam overlay. So this is the same slope over here. Maybe I erase that and write it below. Right? Yeah, it's clear. So same slope, and this slope over here at this particular point is theta C2, right? So let's just write there. So it's theta C2. So let's just write the expression. So at this particular point C, what is my delta C2 and the theta C2 that I have over here? So this is for beam 2. Also remember, since here the load is acting vertically up, the deflection is up, so this is going to be positive over here. So now I have calculated at this point C over here in this figure. So next I have to calculate at B, because eventually the problem asks to find the deflection at slope at B. For beam 1 I have already calculated at B. For beam 2, from the calculations at C, I simply need to translate them to this one over here. So I know that the theta at C2 will be also equals to your theta at B2. So maybe let's just mark that over here, which is equals to theta at B for the beam 2, but the delta over here I have to calculate that delta based on this deflection delta C2 that I have, and as well as this linear line. So this is linear. So let's just maybe make a note of that. So this is a linear variation that we're having over here. So let's just calculate the delta B for at beam 2. Right, so this is just what I have done over here. This is simply this deflection. This is simply this deflection over here plus the slope times this distance. Remember, this distance is L over 2 because this load is acting over the half of the beam. So if you just go ahead and sort of simplify that, what you will eventually get this expression as equals to. So now what I have is that for both beam 1 as well as for beam 2 at the point B, I have the delta for beam 1 and the theta for B1, and for the beam 2 I have the delta at B2 and the theta at B2 over here. Now I simply need to add them to find the deflection and the slope at B. So if I just go ahead and add them, the final answer comes out as So you see both come out as negative. This one makes sense, it will be negative over here because your beam deflects something like this, that is towards the vertically downward direction of y, and your slope also comes out as negative, so that means you have a clockwise kind of a rotation as something like this over here. Right. So I hope this problem example was clear. So this was the case of the statically determinate example where we made use of the standard expressions in the table, but you have to sort of think that how you want to use the standard, because every problem will be not framed into one of these classic examples. You have to make use of these examples after proper amount of thinking, that which things from the table can you take and apply the principle of superposition to compute the moments, to compute the deflections and the slopes. So this problem example for superposition, it deals with continuous beam where you have two spans, 2L over 3, after that you have a roller support and you have another L over 3 over here. And what the problem asks you is to find the reactions and the supports, reactions at each of the supports and the slope at the point. Now this is also an example where your simple equations of equilibrium will not be sufficient to find the support reactions. So you would have to use your the deflection relationships and so on to find the reactions and as well as the slope, right? So we are not going to explicitly solve this particular problem, although we can look at some pointers on how you would approach to solve this problem. Now you see, so since it's a statically indeterminate beam, you have to choose a redundant. Now you can either choose as RA. So here essentially what you have, if you mark the reactions, you have these three reactions which are there, which are RA, RB and RC, right? So you can choose any one of them as a redundant. For example, RA you can choose as a redundant, or RB or RC. Now you see that if we have to be wise in our choice of the redundant to see that which category in these standard tables it follows. Now if you look at the tables over here, it talks about your cantilever beams, and then all the beams which are given are simply supported. So essentially it's probably the easiest to take this beam over here and choose RB as the redundant. If you choose RB as the redundant over here, then you have one beam that is AC, which has a uniformly distributed load W, right? And you have another beam AC where you have the pin supports and a vertical reaction RB over here. So essentially this beam you can write it as two separate beams. So let's take a look at that. What can we write it as? So your first beam, beam 1, so here I'm choosing RB as the redundant. So this is my beam 1, and beam 2 is going to be again the simply supported beam, but here I will have a vertical reaction RB. So now that you have split your beam into two beams, now you see that over here the summation of the deflections and the slope of these two beams, which eventually give you whatever you want in this beam over here. But now you see here, now you can use the tables. For example, here because of this load W, remember this particular load is W over here, because of this load you can find the deflection which is going to happen at this particular point B over here. Now what is the compatibility? Now before looking at the table, what is the compatibility that we are going to use? So we are going to use, see if in this beam over here at the point B, since you have a roller support, there is going to be no vertical deflection. So the deflection at B, at Y at B, that you calculate from the deflection at B at this particular beam over here, or this particular beam. So here if you have to go and mark, so this is your point B and this is your point B over here. So here the downward deflection that you will get at this for the beam 1, and here the upward deflection that you will get, if you add them up, must be equals to 0. So that is the compatibility condition that you are going to use, right? So maybe let's make a note of that as well. So maybe somewhere over here, so compatibility is your y of b, that is your delta at b for the beam 1 plus delta at b for the beam 2 must be equals to 0 over here. And now you can easily use the tables to calculate the deflection at b. You can use this particular row over here, which gives you the equation of the elastic curve. So at here, if you put x equals to 2l over 3, you will easily get this delta b1. And similarly for this one over here, this is the one which is the point load, but now you have to be careful, the point load is acting vertically upward. So for this one, this also gives you, I think, right where you are applying the load, or I don't know, or maybe the equation of the elastic curve, or x equals to a. Yeah, see, x equals to a, that is the right at the point where you're applying the load. It gives you the deflection over here. So you can simply add that up, and you can find the slope at that particular point over here. Now once you will see that this guy over here, once you calculate this delta b2, will come in terms of rb, because it dependent upon the load over here. So that will help you get what is the reaction rb that you have over here once you apply this compatibility. And once you know one of the reactions, the other reactions can be simply be computed from your equations of equilibrium. So I will write down the final answers for this particular problem that is there. You can go back and check whether you're getting the right answers or not. So the final answers for this one comes out as so these are the overall answers that you get. That is, the reactions are the each of the support and also the slope at the point A. See, the slope of the point A also you can easily compute, because here you are getting the value of the slope at A for this point load case, and also for the UDL case that also gives you the slope at the ends. So it's the slope at here as well as here. You can simply add the slopes to find the slope in the final, for the final overall structure that you have over here. So I hope with these two problem examples, one for the case of the statically determinate structure and one for this one, the indeterminate structure, you are clear on how to use the method of superposition, and these tables actually come a lot to your help to find these deflected shapes or the deflections and as well as the slopes.